up your lab notebook, you've just watched several different videos about the different kinds of interference, constructive and destructive interference. And what I'd like for you to do is to add onto your table of contents Cornell Notes, pulse interference. Now remember, the pulse patterns that we are establishing will also work for waves. So this pulse interference could be applied to a more complicated situation with waves, but it's much easier to first look at it with pulses. So because we're going to use the Cornell Notes, it's your choice whether to use the paper, if you've got extra copies of the paper. If you want to go ahead and use just your lab notebook and draw the different areas, that's fine as well. So our topic or objective is pulse interference. And then our essential question is how pulse interference is different. Okay, so our EQ is what's the difference between destructive and constructive interference. Now, hopefully what you're going to write is your notes section is going to be in the center part. Any questions that you ask over on the side, and then of course at the bottom you're always going to have a final summary section. Now you've already seen some examples of constructive and destructive interference, but now what I'm going to do is I'm going to take you through a couple simulations so that you can see it in slow motion. Also, you can chart what happens to amplitude, what happens to energy, and what happens to speed. The last thing that you're going to get here is you are going to get some vocabulary for constructive and destructive interference. And then finally how you can actually chart this out on a piece of paper when two pulses are actually going to interfere. Interference. Constructive interference was the first set of videos that you looked at, and destructive interference is the second kind of video that you looked at. What I want to do is I want you to continue on your note sheet, and you're just going to do a short version of Cornell Notes right here in your lab notebook or on the space at the bottom of your lab. Now what I'm going to show you real quickly is an animation of the first one, which is constructive interference. If you'll notice, we have two pulses on the same side of the equilibrium, so they're both on the positive side of the equilibrium. Now I have this paused at this point, but you'll notice they both have the same amplitude because I gave each one the same amount of energy. Pulse number one is heading towards the end pole, which would be to the right. Pulse number two is heading toward the pulse maker, which is to the left. So they're on a crash course for one another. So I'm just going to slowly step these two in the screen so that you can watch what happens. At the point at which they overlap, in a constructive interference situation, the amplitudes actually add together. They add together because there's more energy at that one moment along the medium. There's more energy, so therefore it's going to have a higher amplitude. Now I'm going to continue to step it so they pass through one another. Now at this point, they now have passed through one another and they are just continuing going in the same direction they were. You'll notice that once they are away from one another, they're no longer overlapping their amplitudes, so their amplitudes are going to remain the same as what they were when they started. You'll also notice that there's no change in the speed whatsoever. The speed, since our medium has not changed, is not going to be affected by our pulse. The size of the pulse, the amplitude, the width, none of that has changed. It only changed at the point at which they overlapped. And that is when the amount of amplitude or the energy actually changed. This is an example of constructive interference. Next, we're going to take a look at destructive interference. The name of this is called destructive interference. Now, if you take a look at the pulses in front of you, they're transverse pulses. The first pulse is on the positive side of equilibrium and it is moving to the right. The second pulse is on the negative side of equilibrium and it is moving to the left. again, they're on a crash course headed for one another. The difference here, though, is that in this situation, one is on the top part of the equilibrium and one is on the bottom part. So again, I'm just going to step it out so that you can see what happens. These two pulses move together toward one another. When they are directly on top of one another, you'll notice that they canceled each other out. And then they kept on going through. So again, they passed through one another, just like what happened with the previous example. However, the difference is that the point at which they overlap or begin to overlap, their amplitudes begin to get smaller because their amplitudes are canceling each other out. The positive amplitude is canceling out the negative amplitude until they're right on top of one another. So at the point at which they interact, the amplitudes change. The difference, however, is that in this case they subtract from each other. If you'll notice, the speed of the amplitude will never change because it's the same medium. The direction that the pulse is moving is never going to change because once it's moving in one direction, it's not going to change until it gets reflected. And then, of course, the pulse's energy is not going to change either. It just happens whenever they overlap that that energy is canceled out.